In the Fermi Estimate What, Why, and How video, there's a bit more to say about bounding guesses. First is the aside about using a geometric rather than arithmetic mean. Due to Fermi estimates focus on the exponents of numbers rather than their actual value, it is important to use methods that have the same focus. When taking an arithmetic mean, one receives unwanted results that diminish the importance of the lower bound. For example, taking the arithmetic mean between 10 to the third and 10 to the fifth power, we get 5.05 times 10 to the fourth power, which may seem reasonable at first. However, if we change the lower bound, such as making it smaller, like 10 to the second, or first, or zeroth power, we get practically the same answer each time. Since the arithmetic mean adds the two numbers, rather than multiplying them, it puts an overwhelming amount of focus on the upper bound, defeating the purpose of the bounding guess. The geometric mean, however, is exactly what we would want. Using our previous set of examples, instead of always getting 5 times 10 to the fourth power, we get 10 to the fourth, 3 times 10 to the third, 10 to the third, and 3 times 10 to the second. The lower bound has a significant impact, one which is as large as the upper bounds. Looking at the math, it is easy to see why this happens. Since the geometric mean uses multiplication instead of addition, it puts the focus on the exponents as desired, taking their average instead. That is why the geometric mean is used. One can go a step further if they want a little bit more detail for their bounding guesses. Say you think the answer may be closer to one bound than the other, whether this is due to some physical property or simply some measure of intuition. Trying to shift the bounds would not be too effective, since a higher confidence in one of them does not mean that the other is incorrect. Instead, one can do a weighted geometric mean. Like a weighted arithmetic mean, where some of the values are multiplied to give them more impact, a geometric mean adds an exponent to some values. For example, if you are twice as confident about the answer being close to the upper rather than the lower bound, you can take the square of the upper bound before multiplying and use a cube root instead. In general, one can use this formula, where the exponents of the two bounds represent your confidence in them, and the root you take afterwards takes the exponents into account. This way, the result is improved, because it adds a bit more detail to the answer with little extra work.